And today's session is on the Doppler effect. I know we have done the Doppler effect when we did, before we did diastolic function and dysfunction. But just going over the Doppler effect is very important, because more than 50% of what we do in echo is the Doppler. And then when we go on um, to vascular ultrasound, majority of that is the uh, Doppler effect. So a basic understanding of Doppler is, you know, we commonly use the scenario if you're at a train station and you're standing at the train station. If a train is coming towards you and the horn of the train is going off. When the train approach you, the perceived frequency is increased, but as the train goes by you and move away, the perceived frequency is less. The actual frequency that's emitted from the horn is the same. So the transmitted frequency is the same. It's just that the perceived frequency or the observed frequency is going to vary whether the source of sound is moving towards you or away from you. So if the source of sound is moving, so Doppler have to do with a moving source of sound. That's what Doppler have to deal with. Moving source of sound. Sound have to be moving. So if the moving source of sound is coming towards you, the perceived frequency is increased. And once it moves away from you, the perceived frequency is decreased. So that is essentially the Doppler effect, uh, in a nutshell. Um, so when the source of waves is moving with respect to an observer, okay, an apparent upward shift in the frequency for observers towards whom the source is approaching. So it's the same thing. The perceived frequency is increased. So there's an upward shift in the frequency for observer towards it, which is approaching. There's no actual change in the frequency of the source. Remember what we said. The classic example is a train coming towards you. If the horn is going in the train, the frequency of that horn is going to be the same. The frequency of the horn is going to be the same. The only thing that's going to change is the fact that the train comes towards you and then move away from you. So, it's the moving source of sound. And so this cartoon sort of depicts it. So when when it it moves away from you, okay, so it moves away from you, and the the perceived frequency is decreased. Remember that the speed is equal to the frequency times the wavelength. So you can work out what's happening in that scenario. So basically, if you're here, the sound is coming towards you, you're going to perceive that the sound is increasing, or the frequency is increasing. Once it move away from you, then it's going to the perceived frequency is going to be reduced. Okay, all right. So that is Doppler. I mean, we did Doppler in details, and we said that when we do ultrasound, if you have the moving, we talk about the blood now. If the blood is moving or any structure is moving towards the transducer, it's gonna give you uh, a signal above the baseline. If it's if the moving structure is moving away from the transducer, it's going to give you a signal below the baseline. So we went into that in details, and think you understand that. Now we're going to move on to something a little bit different. We're going to look at what we call traveling waves and standing waves. Um, we commonly talk about harmonics, and as opposed to fundamental frequency, the harmonic frequency, or the second harmonics. So, as opposed to fundamental uh, frequency. Most of our ultrasound is done using the second harmonics, as opposed to using fundamental frequency. So the images are a bit crisper, but objects look a little bit thicker. So when we talk about traveling waves are, you know, mechanical waves, and we can create these by vibrating objects. So it is actually, when we talk, so the regular waves that you're accustomed to are traveling waves, because again, waves transport energy, and waves are created by the vibration of particles. Okay, the vibration of particles, and that set up the wave phenomenon. So you're gonna the wave actually travels through the medium. Okay, the matter of the medium is not gonna move. So you try and get that concept. The matter in the medium does not move. You get vibration of the particles, which sets up the wave-like phenomenon. Again, these waves transport energy, and the amount of energy that's contained in the wave is directly proportional to the square of the amplitude of the wave. Okay? So the wave will continue until it encounters another wave or a boundary. And we discuss boundary phenomenon. If it moves from a less dense to a more dense medium, the wave is going to slow down. If it moves from a more dense to a less dense medium, it's going to speed up. Okay? Um, Again, that's a very simple way of putting it. But some of the wave, when the wave incident on the boundary, some of it is going to be reflected. Okay, some of the wave is going to be reflected. Um, so when we do ultrasound of any structures, we plug our system in. You have the vibration of your quartz, your piezoelectric crystal. The vibration of the crystals create the sound wave. The sound wave now travels from the transducer or the probe to the structure, and we call the wave that's traveling to the structure, we call that the incident wave. Some of that incident wave is going to be reflected backwards to the transducer. So the sound is going to travel backwards to the transducer, and that sound wave is now going to be converted to an electrical signal, and you see it in the image. But some of the incident wave is going to travel through the structure, and we call that the transmitted wave. Okay? And we spoke about when the wave is transmitted, it is refracted. Okay, it is refracted, so it's gonna bend. When we talk about refraction, is the bending of the wave, and the bending of the wave depends on the density of the medium that it's traveling in. Okay, so that's very important. So traveling waves is the normal wave that you're accustomed to, and you have your traveling wave. Of course, the amplitude, maximum displacement from rest. You have your crest, your trough. You have the wavelength, and the propagation velocity, your frequency period. So this is what your traveling wave looks like. Now we're going to talk about standing waves. Standing wave, it's not really a wave, but it's a wave phenomenon where the wave look like it's standing still. It look like it's not moving. So when we talk about standing waves, these wave phenomenon is confined to a given space in a medium. If you can get, so this is the concept for standing wave. You're gonna get a incident wave. So you get a sound wave and you transmit that sound wave. If that sound wave just in the frequency have to be just right. So at a particular frequency, you can generate a sound wave that when it travels and it strikes a boundary, the reflected wave is reflected in such a way that the incident and the reflected wave interfere and produce a sine wave pattern. So it's not really a wave in the classic sense. It is a sine wave pattern. And when you look at that sine wave pattern, it looks as if it's standing still. It looks like it's not moving. So specific points along the medium appears to be standing still. And we describe what, when we look at it, we talk about nodes and antinodes. So the nodes are point of no displacement, and then the antinodes are points of maximum displacement. So the concept is, for us, we everybody know about a traveling wave. It's your regular wave, but a standing wave, in order for you to get a standing wave, and again, it's not actually a wave, we call it standing wave. It's a phenomenon, it's a wave phenomenon where the pattern look like it's standing still. But in order to get this pattern at a specific frequency, you're gonna create a wave. That's what we call the incident wave. And then when that incident wave travels and reach a boundary, it's going to be reflected. It's going to be reflected in such a way. So we talk about interference. Remember, we spoke about interference. We talk about constructive interference and destructive interference. When you have constructive interference, the simplest one is when crest meet crest, and then the resultant wave is a doubling of the amplitude then. And then when trough meet trough, you get a doubling same way. So when you get a standing wave, the incident wave, that is the wave that you created, or the initial wave, when that wave reach a boundary, it's going to be reflected, and then the incident wave and the reflected wave is going to interfere to produce a pattern which look like it's standing still. Let me just draw that so you can get an idea, because this is how we get harmonics. So this is the concept behind harmonics. Okay, so if this is a boundary, and say we create a wave, we have an incident wave. So we create a sound wave, and it's traveling in this direction. So this is the incident wave, and it's gonna strike the boundary. Okay, when it strikes the boundary, remember, some is gonna be transmitted and some is gonna be reflected. Okay, if the frequency is just right and the reflected wave, so the reflected wave is going to come back in the medium. Okay, it's going to come back in the medium, and it's going to travel in the opposite direction. Okay, so this is the reflected wave now. So if the incident wave and the reflected wave interfere with each other, so that is going to produce the standing wave. That's what we call a standing wave. And when you look, specific points along the medium appears to be standing still. The nodes are the point where, so the node is where you have destructive interference. So you're going to have crest meeting trough. So they're going to cancel each other out. So that's what we call the node. So node is when crest meet trough and you have no displacement. Okay? All right. And then there's antinodes, and we will. All right. So again, so you have your incident wave traveling in that direction, and then the reflected wave traveling in the opposite direction. Okay. So if the waves interfere, okay, then you get a pattern looking like this. Okay. So this pattern is what we call or standing wave. It gives you the appearance that the wave is not it looks like it's not moving. Okay, and then so when you have the interference, when crests meet trough, there is no displacement. So this is what we call the node. And then when crests meet crests, or trough meet trough, you get a constructive interference. So you get antinodes and node. So this is your standing wave pattern. It is, again, it's not an actual wave, but it's a pattern. Okay, so this is your standing wave pattern. So the nodes, these are nodes, these are antinodes. So standing wave pattern is a vibrational pattern within a medium. Specific vibe, so it's only gonna occur at specific frequency. So specific vibrational frequency of the source causes the reflected wave to interfere with the incident wave. The interference occurs in such a manner that specific points along the medium appears to be standing still. The frequencies are known as the harmonic frequencies. So these are what we call harmonic frequencies. So it is the frequency that produces this pattern. And you can have first harmonic, second harmonic, third harmonic, and so forth. So the frequency that this phenomenon occur is called the harmonic frequencies. All right, so again, the nodes are points of no displacement along the medium. So yeah, it's destructive interference between the two waves traveling in the opposite direction. So for you to get destructive interference, you're talking about a crest meeting a trough, and you get no displacement. So that's a definition for nodes. The antinodes now are points along the medium that vibrate back and forth between points of large positive displacement and large negative displacement. So again, this is a node, this is your antinode, okay? And this is what we call the standing wave. Again, nodes are points along the medium that appear to be standing still. You have no displacement. And then the antinodes, points along the medium that undergo vibration between a large positive and a large negative displacement, points of maximum displacement. So that's what you call the antinodes. Okay? Again, nodes are due to destructive interference, and your antinode are due to constructive interference. So again, your standing wave is not an actual wave. It is an interference between two or more waves, and it's actually interference between the incident and the reflected wave. So when we talk about fundamental frequency, so fundamental frequency and the first harmonic is the same thing. So it is that frequency which will produce a standing wave pattern looking like this. So with your fundamental frequency or the first harmonic, you have one antinode. So yeah, you have one antinode. Okay. So there's one harmonic off. So with your the first harmonic, you have two antinodes. Sorry, you have two antinodes. I made a mistake right there. So remember that the nodes are points of node displacement. So you have this, and then the maximum displacement is the antinode. So your fundamental frequency or the first harmonic have one antinode and two nodes. Okay, so this is what we call the fundamental frequency. For the second harmonic, this is what the second harmonic looks like. You have one, two, three antinodes. Sorry, three nodes. The nodes are points of node displacement. One, two, three. And you have two antinodes. Those are points of maximum displacement. So one antinode, two antinode. So the number of antinodes give you the number of harmonic. So the first harmonic, it has one antinode. Second harmonic, it has two antinodes. Third harmonics has one, two, three antinodes. Okay, and so forth and so on. But how you create the harmonic frequency is important. Again, you have to, it is that frequency that will produce standing waves. So it will occur at a specific frequency, okay? Where when you have the incident wave interfering with the reflected wave in such a manner that if you have two antinodes, then this is your second harmonic. If you have only one antinode, then it's the first harmonic. And the first harmonic is what we call the fundamental frequency. So this is what we use for when we did ultrasound back in the days. We now use second harmonics. Okay, so again, it gives you much crisper image, but objects appear a little bit thicker. All right, so again, the number of antinodes give you the number of harmonics. All right, so so you don't have to go into the just know what a node is and what an antinode is. So you have to try and get the concept of when you do an ultrasound, all you're doing is just creating sound wave. The sound wave travel to the structure. So as we said, the incident wave is going to travel to the structure. It's going to it's going to travel a certain distance. It's going to take a certain amount of time. But when it's reflected, it's going to travel the same distance back to the transducer. So, when your wave is traveling, the distance traveled is going to be doubled, because for you to get an image, it has to travel from the transducer to the structure and then reflect it backward before you get an image. We know the speed of sound in different type of medium. The speed of sound in soft tissue is 1540 meters per second. You have to remember that. So you can work out the time, your signal is going to take to travel from the transducer to the structure and back. You can work that out. Um, you can you if you know if you know the time and stuff, you can work out the depth. You can work out depth. That is the distance traveled. So understanding the basics of what's happening, you can do a lot of things. So again, the sound wave um, is going to transport energy. Sound wave transports sound energy, and the wave is going to travel from one location to another location, and it's because the vibration of the particles in the medium. So if we talking about sound in air, the air particle is going to vibrate. If we talk about in the soft tissue is going to vibrate. So one area is going to vibrate and it's going to set up vibration in the next area and then the next area and the next area until you have a wave phenomenon. So the wave phenomenon is due to vibration. Is the matter does not move. So you have to get that concept straight. Um, when we talk about a medium now, it is the material through which the disturbance is moving. So medium could be water, hair, soft tissue, bone, you name it. Okay? And in the medium, you have a series of interacting particles which are going to vibrate. Okay? As we mentioned before, mechanical waves is different from electromagnetic wave in that mechanical waves require a medium, okay, to transport the energy, whereas electromagnetic wave does not require a medium. You can transmit electromagnetic wave in a vacuum, okay? We show that sound wave is a longitudinal wave as opposed to transverse wave. And the definition for your longitudinal wave is when the particles vibrate parallel to the direction of energy transport, okay? Which is different from your transverse wave, where the particles vibrate perpendicular to the direction of energy transport. When we talk, so sound wave is a longitudinal wave, and because the particles are vibrating back and forth, you're going to have areas of what we call compression, areas of rarefaction. Your crest is synonymous with, or your compression is synonymous with the crest, and the rarefaction is synonymous with the trough. Okay, so sound wave is a longitudinal wave. Okay, and you need to know the definition of longitudinal wave versus transverse wave. It just have to do with the direction that the particles vibrate in. And this is what the sound wave looks like with your compression areas, areas of rarefaction. So your wavelength is from compression to compression or from rarefaction to rarefaction. So those of you who do an exam, they always bring this on all ultrasound exams. All right, so that's it. We're gonna stop here, and we will have further discussion in ultrasound physics. There are a few more important topics that we have to cover in ultrasound physics. So on Saturday we will do some more. You need to go over the lecture. You need to have a good understanding of ultrasound physics. You need to know what you're doing, how it works. I'm doing this ultrasound, how it actually works. So that's ultrasound physics. And if you understand how it works, then when you run into a problem, you can work out what's going on. All right. All right. So on Saturday we'll continue. We'll continue. Okay.